Okay, colligative properties. Will change the boiling point and melting point of the solution. And it has to do with the number of particles. Particles, it's important to understand the number of particles. The more particles present, the higher the boiling point, the lower the melting point. And this is used all the time, for example, in your car. The reason why you have to put antifreeze in your cooling system in your car is to make the system boil at a higher temperature. And it's under pressure. The purpose of the cooling system is to bring heat from the inside of the engine out to the radiator so the radiator can dissipate that heat. So the more efficient the liquid is in carrying heat, the better your car will be able to dissipate that heat. So if you look at a graph, okay, it's kind of complicated, but basically we have an boiling point is raised, melting point is lowered. This is why you throw salt on the sidewalk, is to reduce the temperature that the water will freeze at. And sometimes it does no good if it gets super cold, but if it's kind of around freezing, a little below, you won't have any freezing on your sidewalk if you throw it on ice. Horrible for the environment and on and on and on. But anyway, so if the melting point is this, when we add particles, it's lowered. If the boiling point of the solvent is this, we add particles. When I say particles, I'm talking about solute. It'll be raised. And the units we're going to be using are molality, not molarity. I'm going to talk about molality in more detail in a second here. Okay, so basically, again, boiling point's raised. We call it boiling point elevation. Melting point is depressed. So it's melting point depression, boiling point elevation. Okay, and that's under colligative properties. Colligative means stickiness. So the more those particles kind of stick to the solvent, it then affects the boiling point and melting point. More particles, more the effect or effect. And good old intermolecular forces come into play once again. It's like blah, 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 IMS, IMS, IMS. And you'll see that further you go on in chemistry or biology, you'll see intermolecular forces are very, very important forces to take into consideration. So we have attractive forces, intermolecular forces. Okay, so we have the intermolecular forces. Concentration of solute or the number of particles. When I say particles, I'm talking about molecules or ions. Oops. Okay, so freezing point depression is going to lower the temperature. So if we start with a pure solvent, add in solute to make a solution, it's going to be decreased. So we're going to have a change in temperature, delta T sub F. Now, that small italics M doesn't stand for meters. It stands for molality. Meters is a non-italicized M, lowercase. So molarity, uppercase, molality, lowercase, italicized. Okay, molality again is molarity, as you already know, per liters of solution. And the solution includes solute and solvent. Now, the big deal here is this uses mass. This uses volume. Which of those two is temperature dependent? Yeah. If it's not mass, then it's yeah. So volume is very dependent on temperature. Okay. You got temperature. If it's a liquid, the molecules vibrate more, hence it occupies more volume. If it's a gas, mass is mass. Now, the thing about mass, it's a state function. That means if we have 1 kilogram here, and we go to the moon, it still is 1 kilogram. It's not weight, it's mass. Mass is not affected by basically anything, unless you're talking about nuclear chemistry. Okay, so molality is that's why molality is used frequently, because you don't have to worry about temperature. Where this, if you have any values or constants, you have to give temperature and pressure by which these values were obtained. Okay, so again, molality not affected by temperature. Okay, why do you think the value, now this K value, case of F or case of B, freezing depression, boiling point elevation, is determined by the solvent. Why do you think it's solvent dependent? Huh?
Freezing and boiling.
Yes, but why would the K value, which is the effect of either raising it or lowering it, be dependent on solvent? Yeah.
Especially at the concentration.
Concentration, yes. Yes, but not major. That's definitely a factor. Yeah.
The negative properties that you have in that solvent.
Well, why does it depend on what you use? In other words, pentane versus water. Why would it matter? Well, why would it matter? Go back to up to remember.
So see if I'm understanding the question correctly. You're saying that that if you dissolve salt in water or somehow dissolve another solvent into water, the effect will be proportional to the solvent rather than solute, correct?
Yes. Okay. So let's go back to let's go back up here. What's number one? Intermolecular forces. If you change solvent, the intermolecular forces are going to be different. Pentane versus water. Pentane is very nonpolar. That's an exact opposite solvent than water. So your properties of freezing depression and boiling point elevation are going to be different per solvent. So when they give you this constant, this K value, they have to specify what solvent we're talking about. And 99% of the time in general chemistry, we're talking about water. And 99% of the time when you get to OChem, it's not water. I keep giving references to OChem because OChem is so different than general chemistry. So different. Same concepts though. We still have freezing point, melting point changes when we add stuff to a solvent. It's just that it's not necessarily water-based. Okay, so the K value, whether it's KF or KB. So KB is the boiling point elevation. KF is the freezing point depression. One goes down, one goes up. Okay, so that's the equation we're going to be working on. Now we're going to be modifying this, elaborating on it in a little while, but that's the basic equation. So if we're talking about freezing point, this is going to be negative. Boiling point is going to be positive. So we need to know the molality of the system. And then we need to know case of F, case of B, and that's per solute, per solvent. Very specific. Now you can see these boiling points and freezing point changes are quite extreme. And look at carbon tetrachloride. Very nonpolar. Very nonpolar. Okay, it's carbon with 4 chlorides that totally balance each other out. So it's a very nonpolar solvent or chemical. And look at these changes here. Very, very big time. And the boiling point elevation and freezing point depression, you can't predict necessarily. Be like, I mean, these are pretty, I mean, this is bigger than the rest here, but the magnitude is not as great as these guys. This magnitude is huge compared to these other numbers. So it's hard to predict. Yeah. Oh, okay. You just were moving your hand. Okay, so these are going to be, and these are the units of the Ks are going to be degrees per molality. Now, in your lab, you're going to be in the pre-lab and stuff. You're going to be calculating the Van Hoff factor. And that's an I. That has to do with the chemical in the solvent, the solute in the chemical in the solvent. Okay. Now, I kept saying in the beginning, you were talking about colligative property. I kept saying the number of particles. Not the number of moles of particles, but the number of particles. So if we have a particle and when I say particles, this is regardless of whether it's a ion or a neutral molecule. So let's look at so if we have a mole of sodium chloride, we really don't have a mole of sodium chloride. We had a mole of sodium, we have a mole of chloride. So how many particles do I have when I have a mole of sodium chloride? Yeah. If I have one of these, how many of those do I have? One. If I have a mole of these, how many of these do I have? One. How many total particles do I have if I have a mole of that? Yeah. Yes. Basically, twice the number. Twice the number. That's the key here. And if I asked you how many, it would be Avogadro's times Avogadro's number, whatever it may be. Okay. So when this splits up, we really have twice as many particles. Twice as many. Sucrose in water stays sucrose. It doesn't do anything except drive your liver crazy. So this does not ionize or anything. So if you have a mole of that, you have a mole of particles. So the trick is, does it ionize? If it ionizes, you have to figure out how many ions you have after it ionizes. So if this is 1 mole, so if I have sodium phosphate, and a mole of that, how many moles of particles do I have? Exciting stuff, huh?
Not you.
Okay, so if I have sodium phosphate, how many particles? I think ion wise, is this going to break up into ions? Where we have sodium, the answer is always yes, or potassium. So we have 3 sodiums and 1 phosphate, a polyatomic anion. So how many particles total do I have? How many total particles? 4. So of the 3 chemicals up there, sodium chloride, sucrose, sodium phosphate, which has the most particles? Sodium phosphate, so it's going to have the most effect. Excuse me, the most effect, okay? It's going to have the most change because it's has the most number particles. And that's the Van Hoff factor. More expensive. You can use a lot of things, ionic things. Okay, so the Van Hoff factor, is going to be 2, as it goes 1 to 2, 1 to 1, 1 to 4. And the Van Hoff factor is 4 here. So basically what you have to do is you have to take apart your ion. If it doesn't form an ion, it's going to be 1 to 1, like sucrose. Okay, so that's the Van Hoff factor. Now this is theoretically that's a theoretical Van Hoff factor. So Ferguson, well, what do you mean by theoretical? Okay. Like everything in the world, it's never black or white, it's gray. Other factors come into play to make this value not as big. It has to do with the solvent and the solute particles, how they're interacting together. That will change the actual Van Hoff factor. Okay, so Okay, it has to do with the solvent, excuse me, the solvent, solute interaction. The more they interact, the less effective that particle is. So the solvent basically will tone down the effect of the solute. So the I value won't be quite as high. And instead of 4 on that sodium phosphate, it may be 2.9, 3.2, something like that. Okay. So when they say measure, that would be thing as actual. So this now is going to be ferric chloride. Got 3 chlorides for each iron. That's 4 total. But because of the interaction between that and water, probably, it's only 3.4.
Really on topic, what language banned off? Because I don't have any like quotation programs about it.
Just guessing it would be German.
Sounds like it just.
Von Hoff. Yeah. A lot of the earlier physicists and chemists were German. Yeah. Okay, so that's basically what our lab is about. We're going to be looking at freezing point depression and boiling point elevation in the lab. And you're going to be talking about Van Hoff numbers, delta T Bs, delta T Fs. So it should be a nice lab to finish the semester out. Oh, and by the way, Monday is just review day. So it's totally optional, but you need to, lab on Monday is going to be lab checkout, which is not optional. Okay, you've got to be here that day to make sure your lab drawer is checked out. Okay, but the lecture is going to be optional. And then your final will be Thursday. Yeah,
For the lecture.
that'll be totally optional. I don't have it scheduled. I've got Monday scheduled. If you'd like to meet, it'd be the only day I couldn't meet would be the 13th, which is Wednesday, I think. I could meet everyone on Tuesday if you'd like. If there's more than, or we could do a Zoom session. Like maybe a Zoom session would be better on Tuesday if there's interest. And if you're just going over review stuff, that's what Monday's gonna be about.
Didn't he promise the study guide?
No, I was waiting for an email from someone. I read that. No. Send me one though. Just you send me an email. Yeah. I'm sorry? Yeah. It'd be like test 3. I'll try to get it done tonight, probably tomorrow. And then it'll be due the next day at midnight. The same thing. Give you a lot of time to do it. Okay, let's talk about one more topic. We've talked about emulsifiers very, very briefly. So I want to talk more specifically about, instead of soaps, we're going to call that emulsifiers. Soap is an emulsifier, but there are a lot of other things are emulsifiers as well. Every time you see the word soap, it's going to be emulsifier. Emulsifiers are horrendously important all over the place, biochemically, organically, and your day-to-day life, emulsifiers. one question I gave for my uh, my organic class last spring was we're in the middle of a pandemic and everyone's has um, masks and it's fogging up their glasses. So the question was, how does an anti-fog work? And it's very interesting how they work. That was, I mean, just so it's not organic chemistry. It's really general inorganic chemistry, the way it works. Fascinating. After I read how it works, I would have never guessed how it works. So it's really interesting. Okay, so emulsifier. Okay, the molecule's usually pretty good size because it's got to have some kind of a polar end to it. I don't know why they call it a head. Okay, so something very polar. That means it's ionic or COOH or something. Anyway, something very, very, very polar. Got a lot of hydrogen bonding going on, etc. Okay, so that's number one. Number two, it's got to have a very non-polar part. Okay, no exceptions. Emulsifiers have to have both parts to work. I can give you the example of vitamin B12 shot. When I was young, I gave that as a take-home problem. Make this more polar so that it increases the motility of this vitamin in your system. Makes it more polar, that means it can be moved around by the blood much easier. So that's basically it. You need something very polar part. And that's going to be the hydrophilic part. Now, emulsifiers can be used in non-water systems or water systems. So the main thing is hydro, meaning water, philic, love. So this is the part that likes polar solvent. Polar salt. I'm generalizing this because talk about soap by itself is extremely narrow. So this would be and then we need a very non-polar part. And that would be, again, hydrophobic as it relates to solvent. Okay, two parts, a very polar part, a very non-polar part. One's going to fear water, one's going to love water. But it doesn't have to be water. It could be a polar solvent. Let's write polar here. Yeah.
What's the solute?
Huh?
What's the solute in this equation? Is it the water?
The solute's going to be the emulsifier.
Is it the salt?
They're both what? So the solute's going to have two parts.
Yeah.
A very polar part and a very non-polar part. And they always say the polar part's hydrophilic, hydro referring to water. But really, it's loving polar solvent. Loving polar solvent. Frequently, it's water. It doesn't have to be water. It can be anything polar. It can be glacial acetic acid. You know, glacial acetic acid is very polar. It's not water though. So that's why I want to get very generic here. Hydrophobic means terms of, again, against a polar solvent. Hate water. Fears hot water. Fears polar solvent. At least it's not spam. Okay, so emulsifier needs to have two parts, something very polar, something very non-polar. Okay, so an emulsifier okay, so the process of emulsification, we're binding with the emulsifier a polar and a non-polar substance. Sticks them together like glue. My Spanish person is gone. Who speaks Spanish? David, is that a yes?
I'm gonna have.
¿Cómo se dice glue en español? Is it pegadora? It's always nice to have an expert in the class. Anyway, never mind. So think of the emulsifier is glue between something non-polar and polar. Okay. In the case of everyday life, soap is a common emulsifier, and we use that when we're cleaning dishes and cleaning up the kitchen, whatever. Okay. Frequently, your dishes have grease on it, non-polar, and we want to use water to get rid of it, polar. So now we have to bind the grease to the water, and we do that via an emulsifier, aka soap. Now, you can make your own mayonnaise. Mayonnaise is an emulsion of oil and water. To make mayonnaise, you take an egg yolk now, not the whites, just the egg yolk, plus oil, plus dilute vinegar, and beat that up. And the emulsifier, lecithin in the yolk will be used to emulsify the oil and water. Has anyone ever left mayonnaise out on the counter for 4 or 5 hours? What happens? It go, physically, what happens? It does go bad. Yeah, it gets oily and gross. Now, assuming it didn't go bad with bacteria, you can fix it. Adding a little more egg yolk and whipping it up. Fix it. Frequently, who's heard of satay sauce? S-A-T-A-Y. Okay. Have you ever made it? It's a peanut butter based sauce. Peanut butter's got a ton of oil in it. And so what you do, you create an emulsion so the peanut butter stays emulsified. The problem is sometimes it'll break your satay sauce. Just add a little egg yolk to it and whip it up again. Stay. So as you're washing dishes, you form something called a bubble. So in this case, we have a polar solvent and a non-polar solute. If we have an emulsifier present, it will surround. Now the solvent now will the solvent via the emulsifier will surround the non-polar with the emulsifier, non-polar part. So in the case of soap, not detergent, but soap, most people don't use soap to wash dishes. They use a detergent like Dove or something like that. Soap is made from fat. Fat supplies fatty acids. In this case, it's made from stearic acid. Stearic acid is a saturated fat found in animal products. Okay, so if soap's going to be emulsifier, then you have to have a non-polar part and a polar part. So the polar part's going to be the acidic portion of the stearic acid. Now, the reason why they call it stearate is because it's a sodium salt of the acid. If we had an H there instead of this, it would be stearic acid. Sodium there is going to be called stearate. So we have the two parts requirement for an emulsifier. So soap is an emulsifier. It has the two parts. Now when you wash dishes, you use a detergent, not soap. Even though everyone calls it soap, it's not soap. Ivory soap is soap. Would you use ivory soap to wash dishes if you had nothing else to do? Yes. Doesn't work as well as a detergent. A detergent's made from some other kind of chemical, but it's got polar and non-polar parts to it. Say again?
What's the difference between these emulsifiers that make them act different to dishes to bodies?
It has to do with how the difference between the polarities between the non-polarity and the excuse me. It's the difference between the polar and non-polar parts. If something is super polar, or you have multiple sites on the molecule, it makes it effectively more polar. And you have something else that's particularly non-polar. That difference is where the strength of the emulsifier is. And soap is kind of wishy-washy. Great for gentle clothes, wash your hands, whatever. But as far as, another example, when you're washing dishes, like in the dishwasher, you'd never in 100 years use ivory soap in there. You would not believe the incredible mess. I had it when I worked up in Puyallup in Washington. We had a dishwasher for doing lab glassware, and the other teacher put in soap. Soap. It wasn't ivory, but it was like Dawn or something like that. This suds was this high on the floor, and it took hours. It was such an incredible mess. It was, yeah, got that right. So anyway, the strength of the emulsifier has to do with the divergence between the polar and the non-polar parts. Yeah. Say again?
No, I forgot might be just. But.
Or is like powdered soap breathing?
No, it's not that.
It's to season a cast iron pan. Is that,
It's
No,
not
it's
powdered.
Camping, not,
You can put soap.
no, I said camping.
as long as you're
talking-
quick
you're saying
about it and
camping.
quickly dry it, you're
Yeah.
okay.
It's,
Okay.
no, it's not
Right,
like,
cast iron.
Yeah, I've been trained by my wife on cast iron. What? But if it's well seasoned, it doesn't matter. And as long as you wipe it afterwards.
Yeah.
But if it's like new,
I mean, not a little bit of much of like overall slurry.
Yeah, yeah.
They just told us not to do it.
okay, so that's it basically for summer semester, content wise. Yay! Did you find it?
I think.
Ah, okay. After class, I can tell you exactly what it is.
It's a thing.
It's how the pioneers made soap. Okay, they usually had a hog, and they slaughtered the hog, they kept the fat. And to make, which are, the fat is triglycerides. Okay, to convert the triglycerides to the sodium salt of the acid part of the triglycerides, you needed a strong base. So they took soot from the fireplace and boiled water in it, and you ended up with potassium hydroxide or lye. Then you boil the lye and the triglycerides together and soap. Yeah, so the soot from the campfire is valuable. You make lye with it. That's where we're going, right? Yeah.
That's.
My grandma used to make. She had a little farm in Texas, and she'd make her own soap. And she had this cauldron. When you make soap, it's dangerous because you're boiling lye. Here she is stirring it. It's like if she had a witch's hat, it'd be a great picture. Because she's tall and thin, kind of not judgmental. I'm just saying the image as she's boiling the cauldron, stirring it, this big long stick she carved from some old tree or something. I said, Grandma, you know how dangerous it is? Yeah, but we can save money by Yeah, well, that's one of the cool things about her. There weren't very many. She was stories I could tell you. Anyway. All right. So anyway, we have a fair bit of time. So rather than collect in the hallway over there, why don't we just stay here? Or you can go out and do whatever. Just when I have a big bunch of, I keep seeing Sue, the other chemistry teacher, look out. I'm going, she's cursing my class. I can see that. She's not mentioned anything to me, but I could just to be as polite as possible. Okay, so any questions? So next week lectures are going to be, in fact, let's do Monday's lecture review on Zoom as well. Well, you gotta come here anyway. No, never mind. The Tuesday, Wednesday review sessions will be via Zoom. Monday, I'm going to be here, totally optional. Lab is not optional because you got to check out. Yeah,
So what days are exam? I was on the third, right? Or is it the fourth?
Thursday,
Thursday? Okay. And then
whatever that is.
you said there's 2 parts to the exam. Are we doing like a take home for exam 4 then the final Thursday?
Correct. Not, yeah.
Okay. Thank you.
Wait, take home 4.
Huh? Oh, these lab exams. We're not going to have a lab exam. One of the other, Dr. Hay, I got his syllabus. I never taught 1A here, taught it at a lot of other campuses. And I just followed his, and he had 2, and then it just didn't work. So just, the other one's gonna go away, so. All right, so you guys have been a really nice class. I've had a whole bunch of classes in my life, a whole bunch. As far as higher ed goes, I've been doing this for 14 years. It depends on whether it's quarter or semester, but basically summer, fall, winter, spring. I've had about 300 or 400 classes. And one of the reasons I teach is because I like to interact with my students. So again, you guys were really a nice class to work with. I really appreciate it. So, and the other thing, you know, I get a lot of people that dump on young people. They would say, oh, the current generation is not what it used to be. Wah, 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 wah. And I said, sorry, not what I see. Not what I see at all. And so I'm always protecting you guys from these older people that seem to think that the older generation always did it better. When I see single moms with 3 kids getting A's in class and working, when I see students living in cars doing well and stuff, you think that's better than the old generation or worse than the old generation? No, I don't think so. And so anyway, I'm just saying though that one of the reasons I teach is I really like interacting with people that are so on the ball, really focused in their what they want to do in their life. Some more than others, obviously, but it just makes me feel good. I could have retired a long time ago, and I just like teaching as well. But the reason I teach is not because of chemistry. It's because of working with you guys and helping you achieve your goals. Oh, and remember, I do write letters of recommendation as well. So don't be shy about asking. And it doesn't matter if you're a year later or 2 years later, within reason. I got to remember who you are then. But I'd be glad to write you a letter of recommendation. So anyway, so next week is just a 1 day for the lab checkout, and then Thursday will be our final, and everything else is optional.